Hello and welcome again to John's Electrical Science and Principles. Today we're going to discuss how things behave differently on AC as they would to DC. So we're going to have a look at three types of circuit. A circuit with a resistance in, a circuit with an inductance in, and a circuit with a capacitance in. Now normally if we had DC, these circuits would just show a resistance. But under AC conditions, we show what's called a reactance, and that kind of equates to an AC resistance, but you add them up with phasors, and because you can't add them up directly. Anyway, let's talk a little bit about what we're referring to. In a resistance circuit, then it would just be as though Ohm's law applies to it. So you've just got a resistance. And if you look at the waveforms of current against voltage in that circuit, you'll see that the current and voltage start together and they finish together, they reverse together, and then the wave finishes together there. So everything's what's called in phase. And also we can draw it as a phasor using two arrows, or the length of the arrows could mean the values of the current and voltage. So we can actually add these together by using Pythagoras. But in the resistive circuit, what you can see is the current and the voltage are together as they are there, and we say that the current and the voltage are in phase with each other. Now with the inductive circuits are coils, and we see these in industry as motor windings and transformer windings. And the thing is, with a DC, if you switched on, you'll get a magnetic field forming around the coil, and that would stay constant. Now the difference is with an AC signal, you have the magnetic field around the coil, but as the voltage climbs and drops and reverses, the same happens to the magnetic field around the coil. And so that would then create a back EMF. It's just like a generator really. You create a back EMF in that circuit, and it will behave as a funny kind of resistor. And there's a particular word for that, and it's reactance. And for this we call it inductive reactance. Now it will tear apart the waveforms, so the current now will start to lag the voltage. So you have the voltage start, and if you notice, the current peak will be after the voltage peak. So there's a phase difference in them now. And in a purely inductive circuit, you can see now here that the voltage and the current are out of phase by 90 degrees, and the current is lagging the voltage by 90 degrees. Capacitor has got two plates and is separated by an insulator, and it stores charge. Now you have an electric field in the dielectric between these two plates, and that's where the energy is stored. And it's a polar opposite to the inductive circuit. So what happens is, you can see that the current is now leading the voltage on the sine wave. And with that in mind, on our phasor diagram, we can see now that the current is leading the voltage by 90 degrees. And a good way of remembering this, we can use the mnemonic civil. And what that means is, if it's capacitive, I is before V, and if it's inductive, I follows V. So that's an easy way to remember which way round it goes. What we're going to do in the next part is have a look at the actual reactances and how to calculate them. So now we're going to look at how these circuits behave under AC conditions. So we've got an inductive circuit there and a capacitive circuit there. So we want to work out the inductive reactance. So inductive reactance will be XL, and to work out that, it will be 2 pi times the frequency, we'll do a little F for that, times the inductance. So if we drop the figures into that, XL, reactive inductance, is 2 times pi times the frequency, which is 100, times the inductance, which is 5 henries there. So XL is going to equal, I make it 3141.59, and the units of reactance are in ohms. Now let's have a look at the capacitive one. And capacitive reactance is going to be XC, because L refers to inductors and C capacitors. So XC is equal to 1 over 2 times pi times frequency times capacitance. So this XC is going to be 1 over 2 pi, 2 times pi times the frequency, once again 100, times the capacitance. So it's 10, but 10 microfarads. So it's 10 times 10 to the minus 6 farads. So if we check all those numbers into the equation, we get 1 over 0.0062 83185. So if we get 1 and divide it by that, we get a capacitive reactance of 159.15 ohms. And what we find is capacitors and inductors work in opposite ways in AC, and that's why we use them for power factor correction, because one can correct the bad effects of the other one. Now something else that we're going to have a look at as well in our next talk, and that will be impedance Z, and that is going to equal the root of the resistance of the circuit squared plus the reactance of the circuit squared. So if you notice, the impedance takes into account the reactive and the resistive elements of the circuit, and it's working them out in exactly the same way as Pythagoras would. That's Pythagoras' theorem, the root of r squared plus x squared, and this will help you to build up the impedance triangle. But of course in AC circuits it behaves differently to DC, because you've got the reactive and the resistive and the reactive components. And your x squared, if you've got both inductance and capacitance in them, it will be the largest reactance subtract the smallest reactance, and that will give you the overall reactance plus the resistance, square them both and square root, and that will give you the impedance. And what we're going to do next time is have a look at a circuit with inductance and capacitance in it. We'll find its impedance, and then we'll go on to find out its power factor. Thank you very much, and we'll do that in our next time, in our next lecture. Thank you.